I hope that when you began to look at this problem here, problem M, that you immediately recognized that this is just a more general case of the previous problem that we did, problem L. And in fact, the only thing that you really needed to change from the previous proof was simply the language making the triangle an equilateral triangle. So I've removed that language. It no longer says let equilateral triangle ABC be inscribed in the circle, but rather let the triangle, and everything should still work. So let's walk through this and I'll explain. Now this is pretty straightforward, pretty simple. The only trickiness here is in recognizing that we will end up with situations where the center of the triangle, as we've defined it, is not actually within the triangle. Now this seems counterintuitive, and it is, but remember, based on the way that we've defined the center of the triangle, which we've defined somewhat arbitrarily, just for the sake of these exercises, but taking that definition seriously, we do end up with cases like this, where we define a center that is outside the bounds of the triangle itself. And so, because that is permitted by the definition, we have to construct a proof which reflects that. And if you constructed the proof correctly, you would have recognized, I think, that this is the case. Now, if you didn't draw your diagram exactly like this, that's perfectly fine. I drew mine like this just to emphasize some of the strangeness of taking the definition that we have in defining the center of a triangle as a point equidistant from the corners. Because that seems intuitive in the case of equilateral triangles, but once we get into scalene triangles like this one, suddenly that definition begins to look a little bit strange. So the way that I've drawn the diagram here is simply to highlight that fact. So let ABC be a circle, we've got that circle, and D the center, just like last time. Let triangle ABC be inscribed in the circle, and let DA, so a little dashed line here, DB and DC be joined. I say that D, so D is obviously the center of the circle, but we're also going to claim that it's the center of the triangle, even though it lies outside the sides of the triangle. And here again in brackets I've reminded us, if the center of a triangle is defined as a point equidistant from the corners, that's the definition that we're employing here for the center of a triangle. For if DA, since DA is a radius of circle ABC, it is equal to the other two radii, right? We know that. These are all radii because they all fall on the circumference as before. And they all meet at the center D. Therefore, D is equidistant from the corners A, B, and C. And then again, we have the reductio part of the proof here. For if not, then one of these radii is going to be longer. We'll just say that DA is the long one. But if that's true, then of course the other ones are shorter. But that can't be because we already know that their radii and radii are equal. Therefore, D is in fact the center of triangle ABC. And again, remember, this relies upon us assuming as the definition of the center of a triangle any point that is equidistant from the corners. So I hope that that makes sense, and I hope that that wasn't too tricky. This is pretty simple. If you had trouble with this one, it was probably just because of some of the strangeness that arises from taking this kind of definition of the center of a triangle. Now, this is not a definition that you'll really see anywhere else. This is a definition that we've adopted really solely for the sake of these exercises. Usually, the center of a triangle will be defined differently whenever somebody actually needs to present a definition of the center to a triangle. But it is an interesting exercise in thinking, well, what does it mean to talk about the center of a triangle? Often what you might mean would be something like a balancing point. If you think about how you would actually take a triangle and then make it balance on the surface, right? Where's the center in that respect, the center of gravity perhaps of a triangle? That might be an interesting way of thinking about the center of a triangle, but that's not the way that we've done it here, right? We're not asking the question, if we were to cut out this figure, how would it balance? Instead, we're asking the question, given that the center is some point which is equally distant from all the points, all the corners, where is that center? Another way you might try to define the center would be to draw perpendicular lines. You might try to bisect each side and then draw perpendicular lines from that. And that would be an interesting exercise. You may discover an interesting coincidence between bisecting each side and then drawing perpendiculars and the sort of definition that we've created here. And the reason for that coincidence will become clearer as we continue to go through Book 3, but that might be an interesting exercise to experiment with. But that's really all that we have for this particular problem. So again, I hope that it wasn't too tricky. It wasn't supposed to be a trick problem, even though some of the strangeness might have thrown you off, but I hope that you can at least see how it's just an expansion of the previous proof, and because it's an expansion, we just had to make the language slightly more general, which really just meant deleting the word equilateral wherever it appeared, and that was sufficient. So that's it.